Hello everyone, this is Anuttam, registration number 19 BCE 1285, and the topic of this presentation is Byzantine fault tolerance. So, uh, if we talk about Byzantine fault tolerance, so Byzantine fault tolerance is a solution to Byzantine general's problem. So, this is a very famous problem, and the story goes back to 1980. So, the scenario is like this: there was an army which was going to attack a kingdom. So this army has different group of sub-armies around different parts of the kingdom, and they have different generals around this. So all the generals can choose to attack or retreat. So the main thing about this problem, or to win this situation, is that all the generals have to attack simultaneously, or they have to retreat simultaneously. So it cannot be like if two generals are attacking and two are retreating, then they will fail this, and the other kingdom will get to know, and they will kill the army. So, if you go about this problem, so the situation is like this: that each general has its own army, and that each group is situated in different locations around the city they intend to attack. So the generals need to agree on either attacking or retreating. It does not matter whether they can attack or retreat, as long as the generals reach consensus, that is, agree on a common decision in order to execute in coordination. So the generals have to reach a consensus. That is, they have to agree on a decision which the majority agrees with. So it can be like if three are agreeing to attack or if three are agreeing to retreat, so they have to take that as a final decision. So we can consider the following requirements. So each general has to decide either to attack or retreat. So they are independent. They are not depending on anyone else. So it's their decision. After the decision is made, it cannot be changed. So if one general has decided to attack, that's a final decision. He cannot change it. And all the generals have to agree on the same decision and execute it in a synchronized manner to win. So, so the communication problems are related to the fact that one general is only able to communicate with other through messages which are passed by couriers. So they don't have any high-tech mobile phones or any other messaging service. They can only pass these messages to courier. So there are some more factors which comes into this problem due to this condition. That is, the messages can somehow get delayed, destroyed, or lost. So if the courier service takes more time, so maybe it reaches late to the general, or maybe it gets destroyed in the path, or maybe it gets lost. So even if the message is successfully delivered, one or many general may choose to act maliciously and send a fraudulent message to confuse the other generals, leading to a total failure. So maybe there's some spy from the other kingdom who is in the army, and he tries to act maliciously and will send a fraudulent message, that is something which the other generals have not agreed to, and he will just pass on that message to the further generals. So if we apply the situation to the context of blockchains, so each general represents a network node. So in blockchain we have so many nodes. So each general in this situation is like a blockchain node, and the nodes need to reach on consensus on the current state of system. So in the blockchain system, they have to reach on a consensus, just like these generals. So putting in another way, the majority of participants within a distributed network have to agree and execute the same action in order to avoid complete failure. So they have to reach on a same decision in order to avoid complete failure in order to win. So the only way to achieve this consensus in these types of situations is by having at least 2 by third or more reliable and honest network nodes. So we have to reach the majority, that is more than 51%, and also we should have the honest network nodes in that 51% uh, group. So if more than 51% people try to act maliciously, the system will completely fail. So these are the two conditions that we should reach a majority, and those majority nodes are honest nodes. So this is a scenario. These are four general armies, and they are attacking this kingdom. So this is how someone can act maliciously. So we can see there are four armies. So this commander initiates the communication. He sends a attack call to the Lieutenant 2, and he sends a retreat call to Lieutenant 1. So the Lieutenant 1 will transfer this message of retreat to Lieutenant 3, and the Lieutenant 2 will also transfer the message of attack to Lieutenant 3. So now Lieutenant 3 knows that, okay, I got two different messages, so something is not right. What will happen? He will just convey this back to Lieutenant 2 and convey this back to Lieutenant 1. So the Lieutenant 1 will get, okay, something is malicious, so he will convey it back to Lieutenant, let's say, 0. And the Lieutenant 2 will also convey this back to Lieutenant 0. Then they will try to find what happened wrong, and then they will know that, okay, Commander is a traitor. So now we come to Byzantine fault tolerance, also called as BFT. So BFT is a solution to Byzantine general's problem. So it is a property of a system that is able to resist the class of failures derived from the general's problem. This means that a BFT system is able to continue operating even if some of the nodes fail or act maliciously. So the BFT system is error prone to this general's problem. So even if someone tries to act maliciously or even if some of the nodes fail, it will still operate and operate generally how normally it works. So there is more than one possible solution to the Byzantine general's problem, and therefore multiple ways of building a BFT system. So likewise, there are different approaches for a blockchain to achieve BFT, and this leads us to so-called consensus algorithm. So in blockchain, we have this consensus algorithm, and it can be defined as a mechanism through which a blockchain network reach consensus. So the major role or the goal of these algorithms is to reach consensus among the nodes. So the most common implementation which we see nowadays is proof of work and proof of stake. So proof of work is the original blockchain consensus algorithm. So it was the first one, and it came with Bitcoin, and it is used in projects such as Bitcoin and Ethereum. So it is a mechanism that enables users on a blockchain network to reach an agreed truth. So they have agreed something. So it is a mechanism that enables the user to reach on that truth. So a proof of work is essentially an answer to a complex mathematical problem, and it takes a lot of work to create, but it is either easy for others to validate. This is the main point that in proof of work, the node has to calculate some mathematical problem. So to calculate that at first time, that is to create an answer or solution, it takes a lot of work. But to validate among the other that if the answer is correct or not, it is much easier. So Bitcoin was the first blockchain to implement proof of work as a consensus algorithm. So the miners run a computer program which gives each miner an equal chance proportional to their computing power to discover the solution to the next block. So in Bitcoin, when you have to discover a next block, so all of the miners, their chances of getting the next solution is based upon how much powerful their computer is. So they compete to find the answer, which is known as hash, and to the set proof of work parameters for that block. So this hash is a 64 character long answer and is based upon the inputs to the block, such as transactions it contains. So Bitcoin miners search for this hash by combining this input with a random number known as nonce until someone finds the correct answer. Then, when they find this correct answer, they broadcast the solution to everyone on the network, and then those miners try to validate the solution. So once confirmed that okay, this is the right solution, it is added to the blockchain by other miners, which then use this new block as input for the hash needed for the next block. So then this hash will be transferred as an input for the next block. So how proof of work solved the general's problem? So if we go by the context of the general's problem, so this is how it works. So the generals agree that the first plan received by all the generals will be accepted as the plan. So whatever the first plan they get, they will just accept it. So a general solves the POW problem, creating a block that is broadcast to the network so that all generals can receive it. So in this also, a general will get a mathematical problem. They will solve it, and then they will create a block, and that block will be broadcast to other generals. So following the receipt of this block, now when the others got this receipt that okay, one general has solved this, each general verifies and works on solving the next POW problem, incorporating the prior solution. so that their plan adds onto the previous solution. So okay, now we got first solution. Now other journals will try to work on the next solution. So each time a journal solves a peer-to-peer problem, a block is generated and the chain begins to grow. One block found a solution given to input to the other block, then this will keep on happening and the chain will be made. So in time, any journal working on a different solution will switch over to the longest chain. This is one of the most that journals are contributing to and therefore has a greater chance of success. So the rule of proof of work is that whatever chain is the longest chain will be considered as the main chain, and others will be discarded, or they will be made orphan chain. So as the journalists know roughly how long a period of the solution takes to solve, after a set of amount, they will know if enough of the journals are also working on the same chain. So through this process, the journalists can arrive at a consensus of when to attack, can estimate their chances of success, and can prevent multiple different signals to attack being sent simultaneously. Because proof of work takes some time to solve, no journal can send multiple solutions to other journals. Because if a malicious actor has decided to attack, so first he has to solve some problem, then only he can broadcast that attack solution to other journals. Now he is trying to send the simultaneously he cannot send the retrieve also, because retrieve will take other 10 minutes or let's say other 20 minutes to solve, and until that time uh, the first solution will be passed on to all the journals, and they are trying to validate it and then start working on the next solution. Next solution. So this is a chart depicting how this proof of work thing works. So you have the minus create a block, then they create a block puzzle, then they do the proof of work, then they broadcast their solution to the whole network. Then that solution is verified by the miners, which is very quick. It does not take much time compared to solving a block. Then when they verified this, then they start working again, and the transaction will be created, and then the next block, all the miners start working on the solution of the next block. So preventing malicious actors. So the proof of work also prevent malicious actors such as traitors generals from sabotaging the network by tampering with historic messages. So how does it do that? So if we take the example of Bitcoin, so Bitcoin stores the hash signature of the previous block in every new block. So one new block is created. So it will contain the hash of the previous block. That previous block will contain the hash of the previous block. So any change to an earlier block would require all successive blocks to also be changed. So if I do a transaction, let's say if Alice pays 10 rupees to Bob, that transaction is stored. Now in the next block, let's say uh, Yash pays 20 rupees to Rahul, and something like let's say in third block you have A pays 30 rupees to B. Now let's say Alice is a malicious actor and she wants to say that okay, I have not paid 10 rupees, I have paid 5 rupees to Bob. What she will do, she will go to her block, she will just change the number from 10 to 5. When that happens, all the future blocks will be changed, and then she has to work on all the successive blocks to change their hashes, and that will take a lot of time. Until then, all other nodes will reach in some future chain, and maybe that chain won't be a longest chain. They can discard it. So this would take an excessively large amount of computing power, and therefore the ledger is secure from alterations. So while POW is an integral part of current blockchain technology, critics point to a number of problems with the implementation. The two most pressing issues are the potential for centralization and the waste it generates. So it is a very power-intensive algorithm. It takes a lot of computing power and it's very harmful to environment. So there's been criticism about this algorithm. So proof of stake. So proof of stake is another blockchain consensus mechanism that seeks to address the Byzantine general's problem. It was first deployed in 2012. So proof of stake based networks, unlike POW networks, are not reliant on cryptocurrency mining. Instead, they use a technique called staking. So what happens is that users, which are validators, stake funds in the system. So validators who own more coins on a blockchain can validate more blocks and earn greater rewards. The user attempt to validate incorrect transaction risk losing their stake cash. So in the system, we have all the validators. So it depends how much fund they have, and the more the fund they have, the more they can mine further. So if there's a malicious actor who is trying to validate an incorrect transaction, so if the system gets to know that okay, he's a malicious actor, he will lose all his staked cash. So user can stake coins using normal home computers instead of needing specialized machine for mining in a POW-based network. So how staking works in the proof of stake mechanism. So owners stake their native tokens in staking pool. Then the algorithm pseudologically randomly selects the next validator. So it's random. The next validator proposes a block of transaction. Okay, let's take this block and let's put this on the blockchain. So the validators earn a transaction fee. So they do not get a mining price as in Bitcoin, but they just get the transaction fee whichever the transacting party has paid. So the block is added to the chain, and then others validators try to verify and approve the transaction. So if there's anything malicious, they will just report it, and the malicious validator will be put out of the system, and he will lose his stake cash. So now we have this difference of proof of work versus proof of stake. So in proof of work, to add each block to the chain, miners must complete to solve a different difficult puzzle using their computer power. So that is how proof of work works. So they have to have a very high computing power, and they have to solve this. So it takes a lot of electricity, and it's not good for environment. But in proof of stake, there's no competition as the block rate is chosen by an algorithm based on user stake. So on the basis of how much stake they have in the system, an algorithm choose who will be the next validator. So in proof of work, in order to add a malicious block, you need to have a computer power more than the 51% of the network. So in order to change the system or add an incorrect block, we need to have more than 51% of the network power, which is not possible in current situation if we talk about a system like Bitcoin. And in proof of stake, in order to add a malicious block, you have to own 51% of all currency on the network. So you have to spend too much money in order to add a malicious block on proof of stake algorithm. So in proof of work, the first miner to solve the puzzle is rewarded for their work. So a Bitcoin is minted and it is given to the miner who gets to solve the puzzle. But in proof of stake, there's no reward for creating a block, so the block creator fee takes a transaction fee. So whatever transaction fee was there, he just takes that. So if we compare this, so in proof of stake, there's not much competition, and it won't let the miners to have more and more of their computation power, which can degrade the environment. So proof of stake is also a better algorithm, but there is more centralization in proof of stake because let's say if we in terms of Ethereum, if in currently Ethereum has four major mining pools. So if these four major mining pools get to interact with each other and they think that okay, let's attack the network, then no one can save Ethereum and they can undo all the transactions or change the values of their system. So there are other algorithms also, but they are not majorly popular. So these are the only two algorithms which can solve the Byzantine general problem. Objectives of blockchain consensus algorithm. So now we will talk about what are the basic principles and objective which we should focus on if we want to create our own consensus algorithm. So the first one is unified agreement. So one of the objectives of consensus mechanics is to attain unified agreement that all parties should agree on a common objective. So unlike centralized system where having a trust on authority is necessary, users can operate even without building trust in each other in a decentralized manner. The protocols embedded in the blockchain network ensures that the data involved in the process is true and accurate, and the status of public ledger is up to date. So what does this means is that if you go by the traditional system like in banks or our traditional voting mechanisms, we need to have a trust on the central authority who is conducting the agreement process. But in blockchain, we have a distributed blockchain network, which ensures that all the data which is going through it is true and done by the honest nodes, and the status of the ledger is always up to date. So the second point is aligning economic incentive. So when it comes to building a trust system that regulates on its own, we have to align the interests of participants in the network. So a consensus blockchain protocol in this situation should offer some rewards for good behavior and punishment for bad actors. This way, it ensures regulating economic incentives too. So by the second point, it's just a basic human nature that when you perform something good, you expect some reward, and when you perform something bad, you expect a punishment. So a blockchain consensus should also focus on that. And as we have discussed, POW and POS both goes by this rule. So the third point is fair and equitable. So the consensus mechanism enable anyone to participate in the network and should use the same basics. This way, it justifies that the open source and decentralization property of blockchain system. So what does this mean is that everyone who's participating should have the equal right and equal rule, whichever the consensus algorithm provides, and the algorithm should focus on that also. For prevent double spending. So the consensus mechanism should work on the basis of certain algorithms that ensures that only those transactions are included in the ledger which are verified and valid. This solves the traditional problem of double spending, that is, problem of spending a digital currency twice. So this has been a major problem before Bitcoin, and through the proof of work, Satoshi Nakamoto solved the problem of double spending, and the modern consensus algorithm should also focus on preventing double spending. So the last principle is fault tolerant. So another characteristic of the consensus method is that it should ensure that a blockchain is fault tolerant, consistent, and reliable. That means the governed system should work on indefinite times, even in case of failures and threats. So fault tolerant means that in a centralized network, if a database goes down or the center goes down, it causes a halt in the process. But since we are talking about a decentralized network and we have a number of nodes, so even if one or two nodes goes down, the system is still working as it was, and it will continue the data flow and everything. So till here, we have talked about how Byzantine general's problem creates a problem for consensus and how Byzantine fault tolerance solves it. And we have talked about two algorithms, which is proof of work and proof of stake. Proof of work is used in blockchain, that is Bitcoin, and proof of stake is used by upcoming blockchains. And Ethereum is also focusing on using proof of stake in the Ethereum 2.0. And we have also talked about the differences between both. And if you are working on making your own consensus, then what principle you should focus on. So yeah, thank you.